Today is really my true honor to have Professor Santiago Pujol here to give a special lecture, and then I can say some remark, some words before his lecture. I know Professor Pujol very well, personally, and also because I read many papers on Professor Pujol. He is very famous and made a lot of contribution in the area of reinforced concrete structures, especially in the high-strength reinforced concrete structures, which I also study a lot recently. And not just me, but also some professor from Taiwan. Also, we have a team to study the high-strength reinforced concrete structures recently. That we have been benefited from the research result from Professor Santiago Pujol. I remember a couple years ago during the COVID-19 period, in one committee meeting of reinforced concrete design code for buildings in Taiwan, we invited Professor Pujol remotely to give a short speech. I was the chairman, chaired the discussion. His speech is about why in the ACI 318-19 there is a great factor introduced for the development length equation for the high-strength steel reinforcement. But there is a special factor, so that the development length equation, the length has to be increased for high-strength steel reinforcement. And Professor Pujol gave us some short speech explaining why, and so we understand why. So at the end, we made our own decision for our Taiwanese code about this matter. So, yeah, because of his speech, which helped us to make our own decision. And I think we know that recently Taiwan had quite frequent earthquake activities, including last year in April, we have a big earthquake in Hualien, and also this year in January we have another big earthquake in Jiayi. And during these two earthquakes, luckily we did not have many people to be injured or die from the damage of the structures. However, we did have a significant loss due to the damage of the structure, non-structural component, and also due to the damage of the equipment and due to the interruption of the production of our high-tech industry. That part of the loss is actually greater than the loss due to the damage to the non-structural and the structural component of the buildings. So recently, ENCRI has been given two missions, important missions by our government. One mission is we have to help our government to do seismic retrofit to the private buildings to retrofit the damage caused by the earthquakes. And we not only want to retrofit the structural part, we also want to pay attention to the non-structural part. And the other mission is our government asked ENCRI to do something to help our high-tech industry to prevent the loss due to the earthquake in the future, due to maybe the damage of the equipment, due to the interruption of the production. So we have to, ENCRI has to develop techniques to do this, to address this mission. So I think, I believe, today and then in the future couple of days of the lecture about the drift-driven based design, I think can have help us to have some insight to our missions. I think to control the drift is probably one of the things that we can do in order to protect the non-structural component and also the equipment. For the production, I think we need something else. So I believe that the lecture by Professor Santiago Pujol will be very insightful, and I hope that all of you will have a great lesson today and in the future days. So thank you again, for Santiago, Pujol, and welcome all of you to join this lecture. So we prepared some gifts for Santiago Pujol to express our thanks to you to come here. So.
Thank you very much.
And we will have Professor Huang to say some words. Please.
Okay, thank you. So first I would like to show my appreciation to Professor Pujol and come here to deliver a short course, and also Professor O generously offered entry for helping this meaningful short course. So let me make some comment for Professor Pujol. And Professor Pujol got his bachelor degree in Columbia and then studying his graduate school in Purdue. So after get a PhD degree, and Professor Pujol studying from assistant professor in Purdue University, and the year of 2002, and then from assistant associate and the professor all in Purdue. So then served continuously for 15 years, and then Professor Pujol transferred to New Zealand for the University of Canterbury, and a very famous university as well. So currently, Professor Pujol is the director of the QuackCore. QuackCore is Earthquake Research Institute Center. Yeah, it's a kind of big program, national program in New Zealand. In the meantime, I think Professor Pujol served a lot of committee work in the American Concrete Institute, and also associate editor for a very famous journal, Engineering Spectrum. So I think this world famous scholar come to Anchorage is a great honor for us. And to take this opportunity, I would like to introduce some of the relationship of Professor Sousan with Anchorage. Yeah. Because this 3-day lecture, I think that major work may be starting from Professor Sousan and then work with Professor Pujol together. So I think that Professor Sousan was very famous and is kind of leading the earthquake engineering, especially for reinforced concrete structure. And then the first interaction between Professor Sousan and Anchorage is after Chichi earthquake. So in the 1999 in Anchorage, we have a workshop and to talk about the Chichi earthquake. And that time, Professor Sousan submitted a paper talking about the third alternative for proportional of the earthquake resistant building in reinforced concrete. And in that paper is 1999. And they talk about a very famous formula. I think we will meet today is that using the wall ratio times 1 plus half the current ratio should be larger than all the floor area above divided by 1,000. Right? So I think this equation very inspiring, and a lot of Taiwanese scholars they follow and they took this advice, such as Professor Xu Maoxiong, Professor Zhang Jiaxiang in National Cheng Kung University, and they wrote a lot of papers. And then for Anchorage, we started with the school project, and then we follow this track. So in Anchorage, we use the wall area and the current area for our simple survey, also the preliminary evaluation. I think that a lot of engineers, you're quite familiar with this. And I think this is a very good history and the relationship with Professor Sousan. And another story is that in the year 2016, we have a Meiyong earthquake. And that time, Professor Sousan would like to collect all the building damage information around the world. And therefore, Professor Sousan made a phone call to Professor Otani and to say that he would like to send a team to Taiwan to collect the damaged building information. And Professor Tani immediately referred ANCRE as a supporter in Taiwan. So that time, that I think ANCRE cooperated with Professor Pujol in Purdue University. So you send about 10 members, and ANCRE also have another 10. So we have a large team to survey the Melon earthquake. I think this data, building data, now available internationally. So it indeed is a big contribution to the earthquake engineering. So I think that these two stories indeed indicate that Professor Sosen has a strong relationship with ANCRE, and we would like to pay our appreciation, maybe a little bit late, but anyway, I think that's a good memory, for all the Taiwan research, especially in the earthquake engineering. So with that, how about we have a big hand for Professor Pujol?
Thank you very much. That's very humbling. I'm very grateful. I'm here on sabbatical. And as you know, sabbatical leaves are usually several months long. But I had to cut my sabbatical short, so I'm here only for 1 month. I wish I could stay much longer. Taiwan is fascinating, and all of you are so welcoming. I really appreciate everything you've done, and I wish I could spend more time with you. So, this is what we're going to talk about. This is my email. I understand I have to give you a homework, right? So you might need to use the email, if nothing else, to submit your homework. Right, so make sure you get that. And then I was projecting this from the beginning because I created this tiny URL that will lead you to a Dropbox that has the slides and some reading materials. The reading material comes from this book. The book is copyrighted, so I cannot give you the book. But what I gave you instead were, let's say, drafts, early drafts of some of the chapters in this book. But if you get an opportunity to get a hold of the book is a little better. At least the figures are finished and so on. So you can access the materials there. So I thought I should start by talking about how our profession has been thinking about drift. Because the views, our opinions about drift have changed a lot over the years. And it's quite interesting how the opinions have changed. And I'd like to start by referring to this person here. I have my clicker here somewhere. 1 second. I don't like to stay behind this thing. This is a barrier between you and me. Oh, by the way, please call me Santiago. Don't call me Professor this or that. No, forget it. Santiago. Like the capital of Chile. It's easy to remember. Yeah. Okay, so with that, I don't need that barrier. So let's talk about this guy. This guy was Tachu Naito, Japanese engineer, who was trained by Professor Sado. Professor Sado was among the first engineers who were trained after the Meiji restoration, or some political transformation that occurred in Japan, where Japan reopened its doors to the world. They brought people from overseas, some British researchers who trained Japanese in the scientific method. So from all of that, Professor Naito was trained, and he built very good buildings, like this one here. This is the Industrial Bank of Japan. And this caught international attention. this became famous, this building, internationally, because this building and other buildings built by Naito survived this horrible earthquake of 1923, the Kanto earthquake that destroyed Tokyo. But these buildings stood up. So people wondered, how did he do it? And the Americans asked him that very question, how did you do it? So Professor Naito writes this paper, again, almost 100 years ago, to tell the Americans how to build these buildings that survived such a strong motion. And he says, my guiding principle is to make the period small. Make the period small, short, stiffen the building. He says, in that regard, walls are great. He liked walls. And in absence of walls, then braces, steel braces. Because he said, with these walls or whatever framing you can make that is stiff, you can minimize deformation. Minimizing deformation is what Naito said we should have in mind when we design for earthquake. And if you read that paper from the bulletin of the Seismological Society, he will tell you there that you want to minimize deformation because the partition walls get destroyed with not a whole lot of drift, right? Because the doors are going to jam if there's too much drift. Because the facades are going to break if there's too much drift, and so on. What about strength? They asked him. And he said something fascinating. He said, strength, forget about it. You just need to have a minimum. It's not so important. You just need to have some. Otherwise, it doesn't matter. You may have heard the quote from Hardy Cross. You know Hardy Cross, right? Does anyone know from the students? I see a lot of people with a lot of experience, so forgive me. The students, do you know what Hardy Cross said or did? Are you like the New Zealand students? Every time you ask something, they suddenly need to write a lot of things. But look him up. Hardy Cross was a fascinating character. Perhaps the best contribution from Hardy Cross was the moment distribution method, which allowed engineers to analyze indeterminate structures. It was very hard before Hardy Cross, and he made it easy. He made it a problem of arithmetic, something you could solve on a piece of paper very easily. And his method was so powerful that you could use it to solve circuits, electrical circuits, and also to understand water networks. The same method. Water network circuits and indeterminate structures. Amazing stuff. A genius. Hardy Cross said about strength the same. He said, strength is essential. Otherwise, unimportant. And he was talking about gravity. Naito is talking about earthquakes. Naito says, the problem of the earthquake is not a problem of forces. No. The earthquake doesn't push the building. There's no gorilla, pushing the building sideways. That doesn't happen. You move the base of the building, and the building displaces. The problem of the earthquake is a problem of motion, not force. So he said for force, well, look, if you have a base shear strength of, he said 10% of the weight, that's enough. But he was talking about allowable stresses. Back then they were using allowable stresses. Well, in Japan they still use allowable stress. So you could argue that 10% may be more like 15% or a little more in today's terms. But let's say among friends here, that Naito simply said you have to have a minimum strength, otherwise it doesn't matter. Otherwise, concentrate on deformations. And he goes on to say, well, of course, you have to be sensible. You have to have some symmetry, right? You can't have, say, a huge wall on one side of the building and nothing on the rest of the building. That's not going to work. You have to have continuity of these walls from the foundation to the roof, or at least high up in the building. You can't have a wall in one story but not in the next, and so on. Sort of sensible, common sense things. He also said, try to tie everything together the best you can. Try to cast everything at the same time. Use monolithic construction. And this might make a lot of sense to you, because I think most of the construction here is monolithic. In New Zealand, where I live now, they hate monolithic construction. They love precast, and they want to use precast for everything. If you visit me, and I hope you do, you go to my office, you look up, you see precast beams, double T beams, barely sitting on the beams, with very short sitting lengths. Makes me very uneasy. Every time I go to my office, I look up and I say a prayer, and then I start working. The other thing that is amazing about Naito's work, again, this is 100 years ago. The other thing that is very interesting about Naito's work is his rigor when it comes to observation. Medesosen used to say something along the lines of, some engineers like to think, some engineers like to observe. But we should do both, right? And Naito did both. And he observed very carefully. And I wanted to show you this quote because I think it's very interesting. He says, after the Kanto earthquake, he goes and looks at two buildings. One was a frame building, and I edited that because he just had the name of the building here. But that was a frame building, and he compares that with what happened in one of his buildings, a wall building. And he sees in the frame building, there was more damage to the light fixtures. 100% of them were destroyed. These lights that they had hanging from the ceilings with cables, 100% of them were destroyed in the frame building, and maybe half of them were destroyed in the wall building. You were talking about, Professor Wu was talking about the need to preserve equipment and non-structural elements and so on. The need to go well beyond collapse prevention. For too long, we were just worried about keeping our buildings upright. That doesn't work anymore. It's a thing of the past. We need to worry about keeping our buildings functional. Very different thing. And to have a building functional, you need to have lights that work, you need to have water that runs, you need to have toilets that flush, all that. We didn't think about that for many, many years. But this guy, 100 years ago, was already thinking about it. Amazing. And even more amazing, if you go read papers, and I feel very sorry that Professor O read many of my papers, they're mostly boring. But this guy wrote good papers. And if you read all the papers, they will tell you, oh, ceilings and sprinklers and all these other things that engineers seldom thought about. They are acceleration sensitive. You must have come across that term, right? Acceleration sensitive, non-structural elements. Ceilings, things hanging from above, like these lights. Those are acceleration sensitive. And by and large, people say they're going to get more damage in the stiffer building, because the stiffer building is going to see more acceleration. It didn't happen back there, in this one case. And I'll show you other cases where that hasn't happened. It turns out, and maybe we haven't looked far enough, but if you go look for evidence that shows that ceilings and sprinklers and all these things hanging from above get more damaged in the stiffer buildings, if you look for evidence supporting that idea, you can't find it. You find an anecdote here, a story over there. There's always a story of a hospital in LA that got trashed during the San Fernando earthquake. Then they came in and they built very, very stiff walls made out of steel. And then there was another earthquake, and then a lot of non-structural equipment and so on got thrown about, and they say, oh, you see, it's because the building now is too stiff. There is an account by a person by the name Chelavi, who works for the USGS, who says, yeah, I went to this building that had a lot of non-structural damage after the earthquake. I think that was Northridge. This building that they made very, very stiff with steel shear walls. And he says, yeah, there was a lot of non-structural damage, but most of it was because of water pipes that broke. And the water pipes broke in one level, in the first story, or above the first story, not up high, which doesn't make sense because you think the accelerations are larger up high. Anyways, but that's the kind of information you find, sort of anecdotes, one building at a time. But you know, because you've seen the damage that earthquakes cause. You can't make or draw too many conclusions from one case, one building. You have to look at many buildings at a time. You can't find that kind of thing. And this is an exception to that. And then to finish with Naito's paper, he says, he goes and looks at buildings, again, not just one, but several, and he classifies them in terms of period. And he says, oh, the damage correlates with the inverse of period. The buildings with the longer periods have more damage. That's what he says there. This is in the 1920s. In America, people were at about the same time or a little bit later, people, in this case Pujol in Caltech, in Pasadena, people were moving in the opposite direction. Pujol proposes the acceleration spectrum that you're all familiar with as a design basis. He says this is what we need to look at when we think of buildings that need to resist earthquakes. And the acceleration spectrum, of course, decreases, at least in a big range here, the periods decreases as the period gets longer. That's what Pujol says. Sort of the opposite of what Naito was saying. But the Americans see that, and they see what Naito did, and they say, forget Naito. We love this idea that making the period longer lowers the accelerations. That must be good. That's what we're going to promote. We're going to promote buildings with long periods. That's what was said in the first codes in America. By the way, why? I guess it doesn't happen anymore, but initially the building codes were written by seismologists. Why? Doesn't make any sense. You think it should be engineers writing building codes and the seismologists write about, I don't know, the crust and the mantle and things like that. What goes on above the ground, not what goes on. Sorry, they should write about what happens under the ground, and we write about what happens above the ground. Anyway, they felt empowered. They thought they knew, and they thought they should tell us engineers how to design buildings, and they said, okay, well, forget Naito. I guess they didn't understand it, but they understood Pujol, and his beautiful spectrum came from math, not from observation, not from empiricism. And they said, look, it's all about the force. It's all about having enough base shear, and the base shear should be proportional to the weight. And the proportionality constant, they called it the seismic coefficient, C. This thing. And they stick the period in the denominator, meaning the longer the period of the building, the bigger the denominator is, the smaller this letter C is. So the smaller the shear, and in their minds, the better the building. And then there's a K factor there that was sort of a penalty factor. And they specified that penalty factor for different buildings, but I'm just showing you what they have in this, again, early code in America for two types of buildings. The box building, that's the shear wall building. And then they have the moment resisting frame. I went for a run this morning, and it's so obvious. The moment resisting frame governs Type A, at least, right? Every building here has a big moment resisting frame, and they're proud of it. You're proud of it because you stick the frame beyond the last story, right? It's like you want to show off the frame at the top. You can, very, very obvious. The frame governs here. Well, the frame was also a preferred system for these Americans back in the 30s. They give you a discount if you use frame, and they penalize you if you use wall. They didn't want people to use wall. That's what they were saying. So, just think about it. Kanto earthquake happens, they notice these few buildings survive very well. They figure, oh, they were designed by this guy Naito. They invite Naito to tell him what he did. He tells them what he did. They look at it and they say, forget it. He must be wrong. And they run in the opposite direction. That's what they did. And then someone asks him, wait a minute, but that guy told us about deformation. What about deformation? They asked the committee, what about deformation? And the committee, very interesting, they write a short report, like a letter, answering the question. And they said, yeah, we got into a room and we went like this. Because that's what they did. That's still what we do sometimes to design what we do with our building codes, right? We go like this and we debate our opinions. So they debated 3 issues. They said health and safety and whether that's related to drift. The non-structural elements, the damage to the partitions and the ceilings and so on. And motion sickness. I don't know why they were worried, or why would they portray the idea of motion sickness? That doesn't make any sense to me. Motion sickness. We're not talking about taking a trip on a boat here, right? When there's an earthquake. You know better than me what an earthquake feels like. But that kind of shows the ideas they had about earthquakes, right, in their minds. But this is the text in their report, which is here in an appendix. We have it here in an appendix, verbatim, letter by letter. And they said, oh well, so it is true that if there's so much drift, maybe there may be windows that break and facade elements that fall off, and they could hurt someone and affect their health and safety. Therefore, maybe we should think about that as part of our code, as part of our regulation. If people are running out of the building and there's glass falling, they might get hurt. But these other things of protecting the non-structural elements and how people are, that's excessive paternalism. Doesn't matter. It's not a problem. An engineer can use their best judgment. And after all these discussions, they go on to say, none of this deserves to be in the code. And they say explicitly, none of these concerns about drift should be in the code. Use your judgment. Yeah. I mean, we all think we have good judgment, right? But we all make mistakes. And they were not alone. That was the governing idea in the US for decades. Drift didn't matter. So much so that the advisor of Professor Sozen, Nate Newmark, whom I'm sure all of you have heard of, in his book, written with Bloom and Corning, says lateral displacement is seldom a critical thing in a building. 1961. Interestingly, when they wrote this in their book about multi-story reinforced concrete building design, Sozen was working with them. He wrote the chapters on reinforced concrete, while these guys were talking about the dynamics and so on. Clearly, Sozen didn't agree with that idea, or if he did, he must have been skeptical. Because starting pretty much then, he goes on to run a whole bunch of tests. Soon after this was written, this book was written, Chosen hires MTS, which by then was a small little company. Yeah. He hires MTS and asks them, can you make me a platform that can shake like the ground does in an earthquake? And they say, yeah, sure. And they commissioned the first earthquake simulator for sort of big non-structural testing. I understand there were sort of little platforms that people could move around, but Sosen commissioned the first simulator where you could actually build reinforced concrete things that shaken. And he did in the 60s. In fact, that simulator was built at University of Illinois, Urbana-Champaign. And some years after I started teaching there, we heard that they were going to throw it away. Yes, they were going to get rid of it, throw it into the rubbish bin, as they say in New Zealand. Yeah. So we said, what? No, if anything else, that's a historical thing, just conserve it. So we paid, they said, you can have it for free. What we had to pay for was the truck to bring it to Purdue University. Yeah, couple-hour drive, big truck arrives, everything has been disassembled. We didn't know which end was which. So I went to the lab floor and we put it back together. And we connected it to a modern MTS controller and we tried it and it worked beautifully. But with that simulator and all the work Sosen did on it in 1980, this is 81 because that's sort of the official reference, that's when the thing came out, I guess. But in 1980 they held a world conference in Istanbul. This is a picture of Istanbul, which is full of very scary, very vulnerable buildings, by the way. But in 1980, Sosen in the World Conference writes this paper, very good paper, that says, design of concrete buildings with a view to drift control. Drift control. He was worried about drift. This is Mehdi Sosen back then. This is maybe in the 80s. Professor Wang, you know who this hippie is, right? Jack Maley. Yeah, times change. Yeah. And these were the kinds of things they were shaking on their shake table, to call it that way. They're standing on the shake table right there, and they have this concrete frame with big masses. This is a reaction frame just to hold the LVDTs to measure lateral displacement. But see, you can see the amount of drift that these things saw. And chapter 7, I think. Let me double check. That's right. Chapter 7 of the book, which I gave you, I gave you an early version of it, describes most of these tests and describes this paper that Mehdi wrote in 1980. But perhaps the most important sentence in that paper is this one that says, drift control should be the centerpiece of the design for earthquakes, rather than just another check. 1980. Nahito had said the same in 1923. It took so many years for someone to say, yeah, we've been looking at the earthquake spectrum, at least one of them, because you can look at spectrum in different ways, right? You can look at the acceleration spectrum, you can look at the velocity spectrum, or you can look at the displacement spectrum. In a way, what Sosen said is, we've been looking at the wrong spectrum. It shouldn't be the acceleration spectrum, which seems to suggest we should move the building that way. You should be looking at the displacement spectrum, which goes more or less the opposite way. The displacements increase as the period of the buildings increase. That's what Sosen said, 1980. And initially people didn't pay a whole lot of attention, but by now, we've written entire books about the idea. This is, of course, our book. Well, really, it's his book. I was telling Professor Huang, we started to write the book with Mede a couple of years before he died. But we couldn't finish it. So we tried our best to finish it by summarizing his best papers and also compiling his class notes. That's what you find in the book. And then of course, there have been other interpretations of the same concept in a way, of designing to keep displacement small. Drift-driven design is the same as displacement-based design. We wanted to call our book something different because, well, Mede always talked about drift with that name, and also he liked kind of riddles and word plays. So drift-driven is kind of sexy. Not long after Sozen published his work in 1980, the Viña del Mar earthquake in Chile happens. And buildings like this one were shaken with decent intensity, not Chichi type of intensity, not 2 meters per second velocity of the ground, but half a meter per second. And this building was fine. This particular building was just fine after that earthquake. And then after the Maule earthquake, some years later, the building was again fine. We took that picture. I went there with Andres, the boss, and we took this picture in 2010. We had a hard time getting into the building because everyone was in the building, living there. After the earthquake, the building was fine. You could barely find a crack. Very good building. And these buildings in Chile have a special property. They're full of wall, like Naito suggested. So everything that is hatched here is solid concrete wall. In Taiwan, you use a lot of concrete wall, but you use it as partition. Right? Why don't you put some bars in there? You know, then you'll have a Chilean style building. And they're so much better, I think. I'll show you some more data. But these Chilean buildings are very powerful, and I really like this one floor plan because one of the things they will tell you is, well, what about the architecture? You know, we don't want to live in bunkers. Yeah, I don't want to live in a bunker either. But you don't have to. I mean, look, this is a nice balcony, big window, windows all around. You know, just have to work with the architect and make it happen. And not save and cut every corner. Look at the thicknesses of these walls in centimeters. When I do this in New Zealand, the students are like, oh, what's a centimeter? That's 600 millimeters there, 500 millimeters. 1 centimeter is 10 millimeters. Very good buildings. They did very well. In 1985, there were a couple of collapses. In 2010, there was one collapse in this building, out of tens of thousands of buildings that were shaking. It's supposed to give you breaks. I'll stop because otherwise you might fall asleep. I think we're good. I thought we could have a break every 40 minutes or so, 45 minutes. But I think we're still good. Yeah? Chechen, we're awake? Yeah? Okay. All right. But the evidence has not only come from Chile, here's evidence from Japan. This is now from the Kobe earthquake, where the intensity of the motion was much stronger than in Viña del Mar. I got these data from Professor Ichinose, formerly at Nagoya Institute of Technology, now I think retired. These are percentages of buildings concrete buildings with damage. These are all the concrete buildings. You see, they did have some collapses and some buildings in trouble. But look at what happens if you look at these percentages, but only for wall buildings. No collapses, and very small percentages, fractions of a percent, of buildings with severe or moderate damage. Amazing. Night and day, if you ask me. And again, at least my Kiwi colleagues keep saying, oh, but I bet you all the ceilings were destroyed and the sprinklers and whatnot. And I keep telling them, hey, did you go to Sendai after the last earthquake in 2011? It was fine. You could check in the hotels. You could go have dinner at a restaurant. The city was working. Same with Santiago in 2010. The city was working. There was some ceiling damage in the airport. I do remember that. It does happen. You do have to put some thinking about how you install the ceiling and how you fix it. But do you need to compromise the structure because of the ceiling? Come on. If I buy a new TV, and I'm very proud of my new TV, and I install it on a wall, but I'm worried that in the earthquake it might come down, do I buy better fixings to fix my TV better? Or do I go to the basement and start cutting away braces so my house is less stiff and it come on. I'm going to explain this in more detail a little later, but for now, let me just say about this slide that this is some of the data that Professor Wang was referring to. These are data that have been collected after 15 earthquakes or so, including the earthquake here in 2016. So again, we have about data from 1,600 buildings or so. Each dot here represents a building. And I'll go back to this again and explain it in a little more detail, but this represents amount of column, if you will, and this represents amount of wall. And these buildings, this data from all these buildings that we've surveyed after many years, essentially show that if you're above a certain threshold representing amount of wall, if you live up here, very difficult to run into trouble. Very difficult to find a building with a lot of damage. It does happen. There are things that go wrong. Maybe the wrong detail in the wrong place, or maybe some irregularity or something, but by and large, buildings with a lot of walls do well. This is a picture of the cover page of the Turkish building code. And I'm crossing it out because there's a new code that came out after the 2023 earthquake. This was the previous version from 2018. Thick code with lots of provisions and equations and force-based or force-obsessed, right? With reduction factors for ductility and dissipation, all that mess is in there. Very sophisticated. Didn't work. It hasn't worked. In Turkey, at least, it hasn't worked. And they have many challenges with construction quality and so on, but they're essentially scrapping this and replacing it with a code that has 2 pages. A 2-page code, at least for seismic regulations. Of course, there will be more pages about detailing and development things and all that. That stays. But at least for seismic considerations, they have 2 pages. They're just saying, we want you to live above that line. Provision number 1. Provision number 2, keep the limit for the 500-year earthquake, whatever that means, at 1% or less. That's pretty much it. That's the new code. That's the new Turkish code. Let's stop there for a second and see if you have questions. No questions? That's a bad sign. You know? No questions usually mean it's either that everything has been too confusing or that you're still a little too sleepy and you need more coffee. All right. To open up the next presentation. And again, all these files are right on the Dropbox folder I shared with you. There's also the possibility to watch this online. Again, I feel a little bit sorry you have to do that. If you, I understand some of you need to leave later today to attend some other lecture. But I watched some of my own videos online. It's terrible. It's so bad. I can't stand it. So I feel sorry for you if you have to watch my videos online there. This is going to take a little longer than I think we should spend for the next break. So let's answer this question and then maybe let's take our first break. Yes, sir.
So what it appears, or at least in the codes, that there is a very big focus on force-based method, and I think even with the U.S. code and the Taiwanese earthquake code, we only have like this small section where you limit the lateral or the drift to 1/1000th of the vertical height. So, given how much you've said about drift-driven design, like what do you think is the opposition, the main opposition that we face in transitioning from force-based method thinking to drift-driven, or is this something you'll talk about in the future sessions?
I'm afraid I don't have an answer because that goes into psychology almost, right? Look, my best guess is that we started on the wrong foot. We went in the wrong direction. When the Californians discovered the spectrum, it seems we were too mesmerized by the beauty of the math and the elegance of the spectrum. And we couldn't look beyond that. And I'm talking about the acceleration spectrum. We could have very easily looked at the displacement spectrum and arrived at the opposite conclusion. But we didn't. It was convenient to at the time. And this is written. They've said it. That one of the reasons they chose to look at the acceleration spectrum, which suggested longer periods are better, one of the reasons they liked that is that they ended up with cheaper structures. So it was sort of the perfect storm. So in my mind, in California, they went into the wrong direction, and too many other professions or professional societies around the world copied them. And that was unfortunate. I think it was a mistake. And the problem with mistakes is that sometimes it's very difficult to admit the mistakes. It's very difficult to say, oh yeah, you know, all those buildings out there that we designed after all that math and all that calculation, well, maybe we shouldn't have done that. It's very difficult to say that, right? How do you say that to the owners? You know, we just updated the seismic hazard map in New Zealand. And all of a sudden, the hazard you need to design for in Wellington is twice what you used to design for. How do you tell your client that the building you designed yesterday all of a sudden is off by a margin of 100%? You know, these transitions are very difficult. And in this case, we haven't had the guts to admit we should have done things differently. So in the US, I mean, there have been sort of timid efforts. Initially, there was no drift limit. But then we introduced the drift limit, but it's still pretty liberal, 2% in America, 2.5% in New Zealand. And it's like that in many countries. But you mentioned a much smaller number,
Like
1 over 1,000.
Yeah, or 0.005.
But that must be for reduced forces, or are you actually for reduced forces?
Reduce force.
Ah, well, yeah, multiply by the reduction factor and you get the real, the real drift. So if you do that, what's the actual drift you're designing for?
Probably 2%.
2% for the 500-year earthquake, which is the other big elephant in the room, right? When the Turks say, well, we're going to design for 1% of the 500-year earthquake, we should also wonder, didn't you just get the 500-year earthquake wrong? Right? Because the earthquake in 2023 was twice never mind the 500-year earthquake, it was twice the 2,500-year earthquake. You know, what's the probability that's going to happen? Anyway, we keep fooling ourselves that we think we know the demand when we don't. And then on the basis of that very wild assumption, we design for fairly liberal conditions because, you know, we're going to test the building in Tainan next week. And we might shake it to 2% or more. I'll tell you, I don't want to be in that building at 2% or more. I wouldn't mind being in it at 1%. Yeah, we're too liberal. And again, it's too difficult for anyone to recognize maybe mistakes or things that could have done better. That's my best guess. But again, that's a matter of psychology more than engineering, right? Okay, so should we take our first break? Maybe 5 or 10 minutes? 5 minutes. Okay, so I got, how about 15 minutes past the hour? I got 10:08, 15 minutes past the hour, we meet again. Okay, thank you. So that was sort of a perspective of the history of what we've done with drift or what we haven't done with drift. That was sort of the history of what has been done or hasn't been done about drift. Let's talk about things that are more consequential maybe to us. Let's talk first about taller buildings, maybe taller than 5 stories. And I'm going to go back again to Chile. We already mentioned this building, and these were the peak ground accelerations that occurred near that building in 1985 and 2010. But I wanted to show you the actual configuration of that particular building. This is the floor plan. Again, every thick dark line here is concrete. And I find this to be a very ingenious layout because you see the ocean is somewhere here, and these are all balconies, which means every apartment has an ocean view. You can make very appealing buildings even when we use a lot of shear wall. Here's another example of another Chilean building, and all these sketches are on the material I gave you. And as a matter of fact, the reports that were written about these buildings, I'm giving you 2. I'll show you how to access them in a second. I want you to have examples so you can sort of imitate things that I think have worked very well. Again, that's another example of another building in Chile. Notice there are no columns here. Maybe a little thing there that you could argue is something like a column, but by and large you have just walls and flat plates. No columns, no beams. Just wall and slab. That's all. The walls, of course, have to run from foundation to roof, preferably. You could, Jack Maley's thesis, I think, was about whether you need to build the wall all the way to the top of the building. You can discontinue the wall at a certain height, but to make my story easier, let's just say we should have walls all the way from foundation to roof. And in a building like this, again, it doesn't mean that you're not going to be able to see the daylight. You'll have lots of views. That's a photo of these buildings that I showed you already. But once again, you do want thick walls. Thicker walls work better, and we'll talk about why. And you do want to have as much continuity towards the bottom. They do have also architects in Chile that force you to have big openings at the bottom of these buildings for parking and so on. They deal with that somehow. So the question is, how much wall is enough wall? So I want to talk about that in two different ways. First, in this way, where the x-axis here is wall area. So you sum the areas of all the walls, all of them, in one story, and you divide by the floor area of the same story. Let's call that wall density. Okay, wall density refers to only one story. This is number of buildings, so this is just a histogram, and what this shows is that on average, more or less, in Chile, 6% of the floor area is occupied by solid reinforced concrete wall. 6%. Roughly 3% in each direction. Roughly, not exactly, because again, you have architects that you have to deal with, so you don't have perfect symmetry. But roughly 3% in each direction. And that percent now appears here in the y-axis, doesn't vary a whole lot with number of stories. They keep that percent fairly constant for buildings of different heights. You could argue, yeah, maybe the shorter buildings have a little bit less wall, but by and large, all the buildings in Chile have very high percentages of the wall, of the floor area occupied by wall. This idea became known as the Chilean formula. The Chilean formula says 3% of the wall area should be occupied by wall in each direction. That's the Chilean formula. And again, the areas might be slightly different in the two directions, but they're not too different. You cannot put all the walls in one direction. And Professor Juan, we were talking about tunnel form construction, the special type of construction where you have formwork that you can install and remove very quickly. Look it up, tunnel form construction. Tunnel form construction is very good in that you end up with a lot of walls, but the danger is that very often you end up with a wall in only one direction. Cannot have that. This is wall in one direction versus wall in the other direction. This is the one-to-one line. You will see that there's always a direction that has more wall than the other, because, you know, architectural constraints, but by and large, you never have less than, say, for most cases, less than half the area in the weaker direction. Ideally, you should have the same area in both directions. Another way to think about this is to think about it in terms of stress. Axial force divided by area, simple stress. That's what this shows. Total building weight divided by wall area. In these odd units, if you divide by 10, that gives you megapascals. So in essence, what they're saying is, in a typical wall in Chile, if you divide the axial load by the area, you're looking at something between 2 or 3 megapascals. Big deal. Small stress. Huh? While the concrete strength is probably more like 30 megapascals, we're talking about 10% of F prime C. Very small axial stresses. Again, it's all because we have 6% of the area occupied by wall. So how much wall? It's enough wall? Well, for these buildings in Chile, which tend to be taller, again, more than 5 stories, 6% is enough, 3% in each direction. Another way to think about it is to think about it in terms of period. And again, this is once more for the buildings in Chile that were surveyed in 2010 and 1985. So now what we have here is number of stories versus period. And these symbols here represent buildings in Chile. And what you see is that the typical period for a building in Chile is about n over 20, number of stories over 20, while in California and the US, people tend to design for n over 10. And one of the cases I'm going to try to make here is that that simply means that buildings in California are going to drift twice as much. You double the period, more or less, you're going to double the drift. You double the drift, you double the damage, or maybe quadruple the damage. That relationship might not be linear. But roughly, if you don't like the idea of just dividing areas, because that's too primitive, maybe, calculate period. And we're going to do some exercises here to check period. This is a very important quantity in my mind, initial period. That gives us an idea of the stiffness of the structure and the mass and so on. But the Chilean building, by and large, has a period of n over 20. So 10-story building will have a period of half a second. Pretty stiff. And I would imagine that if you measure the periods of buildings in Taiwan, they're probably very stiff too, because of the non-structural wall. Is that right? The problem is the non-structural wall doesn't have any deformability, so it gets damaged very quickly, and then it leaves the soft story where you interrupt it to create space for your wonderful stores where you can buy all sorts of delicious things like stinky tofu. Right? If you're interested in those reports and all the data about these buildings, there, that's yours. These slides are, again, in the first URL I gave you, which was the same thing, http://tiny.cc/drifter. All right. So that's what they did in Chile, or what they saw in Chile in 1985 and 2010. Mostly, again, in taller buildings. Let's talk now about shorter buildings. And I'm going to refer back to the Hassan Index that Professor Huang mentioned before. Hassan and Sozen proposed their indices, really, they have 2 indices, because they had cities like this in mind. This is Kathmandu in Nepal, where there are many short buildings that are not built very well. And they are vulnerable, and their idea was, or their question was, what do we do with these buildings? We need to fix them, but we can't fix them all. At least not at once. We need to start somewhere. And the question they were asking is, well, what building should we fix first? And they used some data to propose some indices that I'm going to show here in a second. The initial data they used was compiled in Turkey in 1992. But since then, we've been compiling a whole lot of data. And as Professor Wang mentioned, we came here in 2016 to collect more data from buildings in the south of Taiwan, including district office buildings. Like this one, we collected data from Nepal. where we go, and if we get drawings, then we can measure areas of columns and areas of walls to try to look at densities and numbers that can tell us how much wall and how much column there is. And then we try to classify the damage to see if there's any correlation between, in a way, stiffness and amount of damage. But short of, or not to calculate periods, which will be more involved, what we've been doing is using these indices. So I showed you this index before in one of the plots, but I showed it to you, and I simply said that refers to amount of column. But this is the shape of the index in more specific terms. So what we do is we go to the floor plan and we measure all the walls, all the columns, and we add up all the areas of all the columns. This is a calibration coefficient. And then we divide that by this. So for those of you who have to submit the homework, you got to be careful here, because this is a place where you very often make a mistake, or it's very easy to make a mistake, I should say. This is not the area of one floor. This is the area of all the floors above the critical floor, which is usually the ground floor. There's a summation there of all the floors. This is also summation, but it refers to the columns at one floor only, right? So this is for one floor, this is for all the floors. Very easy to make a mistake there. And that's how we quantify amount of column, again with the idea of estimating how much stiffness and strength maybe something has. And then for walls we do something similar. We don't have the calibration coefficient of 1/2 here, which suggests walls are more effective than columns. And some credit is given to the infill, because it does seem to help. And in Taiwan, I think you use a very similar index, but you do a little bit more work here to give more credit to things that are better confined by boundary elements and so on. So what we've done is we've gone to places again like Taiwan, and we've classified the level of damage. When we see something like this in one of these buildings, we say that's bad. Right? Doesn't look very good. We call that severe damage. And this is essentially the same plot I showed you before, where once we survey all the buildings, we say some are not so good, some may be okay, at least damage-wise. That doesn't necessarily mean that the building will be okay for the next earthquake, and we can talk about it. But the idea is all the yellow dots here represent buildings that got in trouble. Again, this is amount of column, this is amount of wall. And once more, if you are above a certain level here, it's very difficult to see damage. You could also draw a line at an angle here and say, oh, if you're outside that corner there, you see less damage. But what I really wanted to show you is how you can, to use sort of a phony word, how you can deaggregate the data. These are all the data from many buildings surveyed after many earthquakes. But I wanted to separate the data from different places. So this is the same plot, but for buildings from Chile only. Column index is essentially 0. Again, you saw the floor plans. They don't use columns. So that's why you're pretty much at 0 here. And then they use a lot of wall, and you see very few buildings represented by red squares, which means very few buildings with damage. That's Chile. Here are data from Japan from 1968, data collected by Professor Shiga over there, who proposed pretty similar indices to be used in a different format. He went around in 1968 in the Tohoku region up in Sendai and collected data that we could translate into column index and wall index. And this is what we see. So relative to Chile, you can see the dots move to the right. Sorry. Meaning you have column, but you also have a lot of wall. So the Japanese have a lot of wall and columns too. And this is where you are, Taiwan. These are the data from 2016. These buildings, at least the ones we saw down south in 2016, are not so generous in terms of wall, right? And I'm guessing all these other walls that we classified here are mostly partition walls. But what you see, I think, is you realize more red dots representing buildings with severe damage start showing up. They start showing up near the origin. And then this is what happened in Turkey in 2023. In Turkey, they really go close to the origin here. So they're building buildings that are quite tall, up to 15 stories, with very small, in relative terms, columns and walls. And they get into a lot of trouble. Once again, if you put it all together, you could argue that if you're above that line, your building should be okay. And interestingly, that idea is being picked up by agencies. It's not just us, people who work with Professor Sozin and maybe people in Taiwan who say that anymore. Now, even the almighty US government is buying into the idea. So these guidelines, published not too long ago, they're meant to help engineers evaluate or assess buildings. And of course, it's, an engineering document is not always the simplest thing to read. They make things a little bit more complicated, but the essence of the document is if you're above this line and you're assessing your building to see if you need to do anything to it, the guides essentially say, forget it, you don't have to do anything. It's okay. Again, the terms are not quite as simple. It's a little bit more complicated, but in essence, FEMA, the almighty US government, well, it's not so almighty anymore, is it? Rather a confusing government. Well, the US government, is, at least through the FEMA regulation, is saying if your building lives above this line, you don't have to do any lateral load analysis or anything, it's fine. Forget about it. Yeah. I want to maybe stop there and ask for questions. Okay, let me summarize for you roughly what I've been saying. In drift-driven design, we want to limit drift. We want to control drift. And we're going to try to do that by controlling the period of the structure. And the most efficient way to control the period of the structure is to use structural wall. The moment frame tends to be too flexible. But we'll study both. We'll do a few numbers and compare frames and walls in terms of period. But before I go there, before I try to estimate with you, and by the way, for our meeting tomorrow, if you could bring your laptop, especially if you have to submit a homework, if you could bring your laptop, and if you could install ahead of time this software, that'd be great. Maybe you can do numbers with me together. It'd be very cute if we did that. Kind of romantic. If you could install this software called MathCAD Express. It's free. They just put a watermark on your document, but it's very powerful for engineering calculations. If you bring your laptop, maybe we can do some numbers together. But before we go there and we start looking at periods and drifts in buildings, oh, I should also mention, if you bring your laptop and you're going to install a couple of things, maybe you can also install this software. This is a Japanese nonlinear analysis software called Stera 3D. Again, free. But before we go there, I think we need to clarify something. Because we're saying we're going to control drift. Do I have to get out of the room too? Sorry. So, we're saying we're going to control drift by controlling the initial period. But that's a difficult idea, because the period of the building changes, right? So, which period should we use to try to estimate drift? Right? Do we look at just the initial period, or do we try to think of how the period changes during the earthquake? How do we do that? So to address that preoccupation, if you will, and to decide whether we can rely or even think of drift by using the displacement spectrum, which you also calculate by assuming things are linear and you don't, period is only one and it doesn't change. I think we need to talk about the differences between linear and nonlinear response. So I have another PowerPoint here that will help me with that. So the first thing I like to do is refer to the work of this person by the name Shimazaki, who also worked with Professor Sozin. What he did was to analyze all these single degree of freedom systems. As you can see, the single degree of freedom systems have different hysteretic properties. Some were nice and elastoplastic, some were not, but had sort of nice fat hysteretic loops. And then as you make progress, you end up with some systems that have a lot of quote-unquote pinching and things that usually we think of as being very negative for response. So what he does is he takes these models, to call them that way, and he subjects them to numerical shaking, and then he sees which of these things drifts more than the others, right? And he tries to make that comparison on the basis of a common denominator. He wants to compare with the same reference all the time. And for reference, he uses the linear oscillator, which of course will have a load deflection curve that will be just a straight line going to infinity, right? The linear oscillator has not only constant stiffness, it also has infinite strength, right? These oscillators, in contrast, have limited, finite strength. So these oscillators will soften over time, right? Because you might have this much stiffness initially, but as the oscillator drifts and yields, then the effective stiffness becomes much lower. And then the question becomes, well, when you lose stiffness, are you going to end up getting more and more drift, right? Is the nonlinear oscillator prone to more drift? That was the question that Shimazaki was trying to address. And he did so by making these plots, which are very smart, very ingenious, but not the easiest to read. So let me try to walk you through that. You see 6 plots, starting with this one up here. I need my pointer. There. You need to read this from the top first, going left to right, and then you read the bottom. The idea is these first plot refers to an oscillator with a short period. And then this oscillator refers to, or has a longer period, and so on. Longer and longer period as you move this way. Okay? That's why they have different plots. The next thing I need to explain to you is the x-axis, the strength ratio. That is the strength of the oscillator, the maximum force the oscillator can take, the yield force for the oscillator, divided by the maximum force a linear oscillator with the same period will see. That makes sense? Is the ratio of, say, this value here divided by the maximum force that a linear oscillator with infinite strength will see. You can think of that as the inverse of the force reduction factor, if you will. So here, at an ordinate or abscissa rather of 1, you have a linear oscillator, infinite strength. And as you move towards the origin, you have less and less strength. This would be an oscillator with 0 strength, which wouldn't make sense. I mean, we have to admit, there has to be some lateral strength. But he went pretty low here, huh? He went pretty low, pretty close to the origin. Okay, so that's the x-axis, and that's why we have 6 boxes here. The y-axis is the displacement ratio, which is the ratio of the displacement of the nonlinear oscillator to the displacement of the linear oscillator. So an ordinate of 1 here means the linear and the nonlinear oscillator drifted the same, right? Values above 1 means the nonlinear oscillator drifted more. And I think the trend is pretty clear, for the most part. In my mind, this says, unless you have short periods and very weak structures, and I'll tell you, that's very difficult to find. That would be a very short building with very, very weak columns and walls, or even without walls. It's very difficult to live here. But otherwise, these ratios of displacements are all are around 1 and fairly independent of strength. Amazing. How can that be? You can make an oscillator yay strong or twice as strong, doesn't matter. Unbelievable. Yeah, that means I can take my building and put more longitudinal reinforcement in it, or maybe take some bars out. It doesn't matter. That just blows your mind, doesn't it? Because it tells you why are we running so many numbers to calculate the strength of things. In displacement-based design or drift-driven design, strength doesn't matter. Of course, you have to have some. And if you have a building with a short period, you have to be careful. But that's easy to do. And even more interesting, when Shimazaki looks at this oscillator, the skinny oscillator as opposed to the fat one, yeah, things don't change much. You know, every paper out there that says anything about pinching says terrible words or things about the pinching idea. Oh, not enough energy dissipation, woo, big deal. But it's not that critical. Again, unless you have an oscillator or building with a short period, not that big of a deal. That's hard to believe, but it happens. And one of the examples you will find here is this one. These were tests done by Dan Abrams, 1979, to test that very idea. Dan tested a frame connected to a wall. The wall dominated the response of the system. It was a strong wall or a stiff wall. And then say he obtained the black line from that system with a strong wall. And then what he did is exactly what I just said. He took, from the wall, he took, out of 4 bars, he took 3 out. So we made a wall that was in a way 4 times weaker. A wall that had 4 times less reinforcement. And he shakes that thing again. And you get almost the same. Or even less displacement. How do you like them apples? Hard to believe. But that's what happened. And one of the things I want to do with you tomorrow when we meet again is just sort of test that with this cute software from Professor Saito in Japan. I understand this software is based on an initial version of that was called sake, like the drink. That program called Sake was written by Professor Otani, whom you mentioned. And from that, Professor Saito has created this, which has a nice, very friendly user interface. So my hope is that tomorrow when we all have, well, or many of you have your laptops, we can create a new building here and run this idea, or run a test where we can add or remove bars from columns and beams and see if we get more or less drift. Everything has a limit. There are places where things are going to break down. Again, especially if you have short periods, strength does make a difference, at least with respect to linear response. But there are easy ways to cope with that. And in my mind, the best way to cope with that was proposed initially by Bonacci in his thesis. John Bonacci also worked at the University of Illinois with Sozin. He tested single degree of freedom systems. We've talked about Bonacci's work. He was trying to test oscillators with short periods. So the dots here represent displacements that he was measuring in the lab. His setup was complicated, but in essence it was a mass with a beam resisting the earthquake demands. And then he would do different things with the system. He would put bigger mass or smaller mass, and that's how he was changing the period. And he would also use smaller bars or fewer bars in the beams, or more bars, and that's how he would change the strength. And what you see here is something very, very interesting, I think, which is if you look at the displacement spectrum, this is, of course, the shape of the linear spectrum. These are the measurements from the nonlinear oscillator that Bonacci was obtaining. What Bonacci suggested is that the nonlinear oscillator, yes, they can deform more than the linear oscillators, like in these cases, but you can capture how much extra deformation occurs in this problematic, so to speak, short period range with a straight line there. Which simply means, to put it in very simple terms, that yes, we may be able to control drift by controlling initial period. We don't really need to worry about how the system is going to soften. You know, the nonlinear and the linear oscillators tend to drift the same. In the short period range, things can be different, but that's okay. We can take care of that by simply assuming that the drift is linearly proportional to period. So all we need to say is drift can be assumed to be linearly proportional to period, some type of constant times period. That's going to help us find the drift in the building. Amazingly simple. Strength, you have to have at least a minimum, otherwise it doesn't really matter what you have. So what I would like to do next, let me check. But I thought what I wanted to do next is then talk about how are we going to estimate periods and how are we going to estimate strengths to make sure we have at least the minimum. Before we go there, there's another thing I want to show you. I'm going to move this over there. But maybe before I do that, let me ask if you have questions about this or that. Or that. Yeah.
A lot of Southern work, earlier work, talks about these things based on a term called characteristic period. Do you have any idea why at the time they found that thing is a very key parameter to get all of this?
Well, Southern loved to normalize things.
Yeah.
I think he learned that from Newmark. Newmark always normalized displacement relative to the yield displacement.
But he is not using that.
He doesn't use that. There was really no reason either for Newmark to normalize relative to the yield displacement. It was just convenient, right?
Mm-hmm.
And I think Southern sort of inherited that idea that it's better to normalize things. So when he talks about period, he's always referring into this thing that they call the characteristic period of the ground. They said it had to do with the velocity spectrum and the energy in the system, right? But by and large, at least in many applications, in many instances, they were also assuming that that's simply the transition period between the constant acceleration region and the constant velocity region in the spectrum. They thought it had some meaning, right? Because of this argument about energy. But frankly, I think this observation, which is independent of the value, is more powerful.
Yeah.
Because it's easier. I don't need to know that value.
Correct.
All I need to do is draw a straight line here, and that gives me an upper bound for the displacements in the nonlinear oscillator. Brilliant.
Yeah, it's difficult to define that TG term in a real event.
Very difficult to find that because you have to look at a line going like this and say, oh, here's where we go from constant this to there's nothing constant in the line. Yeah, it takes a lot of imagination. So I tend to shy away from that number.
Okay.
Very difficult.
Thanks.
But again, at the end, if you and I agree that we can just draw a straight line here as an upper bound, then it's easy.
Yeah.
I don't need that value.
Correct.
Okay, other questions? Yeah.
Can I ask about the previous slides? So, I think in one of the slides you mentioned about the previous. I think in one of the slides you mentioned about the formulation of the wall index, right? And then in the equation there is like a RC wall, the amount of the area of the RC wall. Is it limited to the structural wall like 18 centimeter or 20 centimeter RC wall, or does it also include the like 15 centimeter RC partition wall?
Concrete, I think when we surveyed, concrete was concrete.
Yes.
Whether well reinforced or thick or not, concrete was concrete. When we've been surveying, how do you treat it here in Taiwan? You put it as infill? That condition of the wall that is very thin and poorly reinforced and so on, and used as a partition, we've never encountered anywhere but in Taiwan. It's not so common. And they use it in Japan sometimes too, right? But in our surveys, Every time we encounter concrete, we call it concrete. Other questions? Now you get better correlation calling it partition here, huh?
No. Reinforced concrete wall we treat as a concrete, and only the brick we will consider 4-side confinement, 3-side confinement.
So the same as us.
Yeah.
So concrete is concrete, no matter how thick or well reinforced it is. Okay, good question. Another question. All right. Yeah, so the other thing I wanted to show you before we start thinking about how we calculate period is some of the measurements that were made by Sozin and all the people working with him, all the graduate students working with him back in the 70s and 80s, because I think it's very informative. You know, when we were looking at these things, we were looking at calculation results, right? It's dangerous to live only in calculation world. One has to look at the actual thing, and that's why NCRE is such a powerful institution, because you have the means to test big buildings and see what actually happens. Let's look at one of these models that were tested by Sozin and his associates, because again it's informative. So what you have here is a stack of plots for one specific structure, H1, and you have displacements at level 2, level 4, level 6, and so on. This would be the roof right there. The building clearly doesn't have a single period, right? That response is not the response of a single degree of freedom system. You see all these little hiccups and things that suggest that there are other modes sort of polluting the response from the first mode. That's obvious. The single degree of freedom system is not an accurate representation of the actual system. So we have to keep that in mind. When we look at spectra, we're working in Wonderland, right? Another thing that is interesting here is that clearly the dominance period is elongating, right? During the earthquake, the period gets longer. It's this short to begin with, but later it's much longer. That should be no surprise, right? Because these concrete structures or models of structures are cracking and they're yielding and so on. They get softer. The other thing that is interesting in this plot is that the sort of small oscillations that are introduced by the higher modes don't seem to have a large amplitude. If you look at this long enough, here's another building. This one, if I remember correctly, this one had a wall. You can see it's much stiffer, it has a much higher frequency. It's a much shorter period. And then the higher modes, maybe the second mode does kick in every now and then, but it doesn't seem to cause big trouble, at least not in terms of displacement. Right? And even better, they have some very cool plots here. This is, again, all from here. This is chapter 7, I gave you that. This is all extracted from that paper from 1980 where drift-driven design was first proposed. If you scroll down, you find plots like these, which I find fascinating, very cool. This is the deflective shape of the structure, the mode shape, calculated using linear analysis. This is one particular structure that looks like a frame, with maybe a first story that is a little stiffer than the other stories. That's what was calculated, again, from linear analysis. From this calculation, you can calculate story drift divided by mean drift, which is what they've done here, right? So this plot sort of shows you the distribution of story drift implied by the mode shape. So this is also the result of calculation. This is also the result of linear analysis. Now these two things are pretty much the same. They tell you how the deformations are distributed in a linear representation of the building. Now this is where things get interesting. This is what was measured. And I would say these two don't look very different. The drift occurs in the actual building, which again cracks and yields and so on. And the nonlinear structure, unless you have failures that start concentrating the deformations in specific stories and so on, unless you have something like what Tomomi Suzuki tested, that was begging for concentration of deformations. The distribution of drift that you would assume from linear analysis is not too different from the distribution of drift that actually occurs in the nonlinear building. That's great news. That's great news. Because if we put everything we've said together, we can say if we're going to limit drift from the work of Shimazaki, it seems we can work with the initial period. We don't need to try to figure out how much period changes over time, how much the structure softens as it cracks and yields and so on. Don't bother. From the work of Shimazaki. But that's again just for a single degree of freedom system. What this implies is that for the multi-degree of freedom system, you should be able to assume that the distribution of deformations is what you would get from linear analysis, which is also very powerful. All this is pointing in a very simple direction, which is linear analysis can give us a lot of good ideas here. And then I wanted to mention one more thing. The other caveat that we've said is that the one place where we need to be careful with linear analysis, maybe the most, is this place, the short period range here, that we usually refer to as the range of nearly constant acceleration. That's where things deviate from what we expect from linear response. You can get more there. But the solution is easy. Just project. Work here the same way you work over there. Project out as a straight line. Use a spectrum, a linear, a straight line as a displacement spectrum. That's it. That's beautiful. That makes it very simple. Okay, so how about we take our second break, unless you have questions. No? Okay, so maybe meet 20 minutes past the hour. Okay, great, thank you. Okay, yeah, recording?
Yes.
So, more than 100 years ago, Naito said, control the period. We debated whether we should look at the initial period or not on the basis of the work of Shimazaki. It seems it's good enough, right? But I thought I should offer another explanation, and this also comes from work by Sozen. In this case, work with Professor Shibata from University of Tohoku University. They, back in the 70s, they wrote a design method that they call the substitute structure method. Later on, Sozen would essentially abandon the idea and come back to just linear analysis as the main way to control drift. But for historical purposes and also to try to understand what's going on, I think this picture is very informative. Why is the initial period a good enough measure of the stiffness of the structure, essentially? Why don't we have to take into account the softening caused by cracking and yielding and so on? So the idea is the following. Think of the displacement spectrum again. Period of displacement. We agreed on the basis of Bonacci's work, and then later on, I should have mentioned this, Andrés Lepage did a lot of work to sort of make the same point. On the basis of all that work, we're saying we're going to assume that displacement spectrum is just a straight line like that. Okay. So the idea is if you have an oscillator with a certain initial period, this is the displacement, right? As the structure cracks and yields and softens, the period gets longer. All the data we've looked at suggests you don't get proportionally larger displacements. You get almost the same displacement. One way to think about that is to say, well, the damping must have increased. If you increase the damping, because there's area under the load deflection loop, then that's what allows us to operate down here as opposed to up there. Is the increase in, if you will, hysteretic damping what helps control the drift as the period gets longer. A longer period should lead to more drift, but it doesn't, because as the period is elongating, the damping is increasing. Those two things have counteracting effects. It's amazing. It's a miracle. No one planned this, right? It just happened. And we should be very grateful that it happened. And every time we change something in our industry, we should wonder if we are moving away from the realm where this happens. When we introduce high-strength steel, when we introduce now maybe FRP steel, or not steel, reinforcing, well, can we operate in the same way? I don't know, those are areas of research. But that's one way to think about the idea that it's easier to operate here than to operate there. We don't have to guess increases in damping. We don't have to estimate elongations in the period. So might as well use this. That's one way to look at the problem. Another view that you will find in the literature to explain the same idea comes in the shape of a slightly different spectrum. This is the capacity spectrum. Are you familiar with the capacity spectrum by any chance? Yeah, Professor Wang is nodding, but the students are going on. Are you familiar with the capacity spectrum? Right? So you know you have SA here and SD here, right? And you might have an initial spectrum like this, but again, because the structure yields and so on, the damping increases, so you reduce the response and you bring it in, so to speak, like that. You shrink the spectrum because of increased damping, and the idea is that if you manage to express the load deflection curve for the structure in terms of acceleration and the spectral displacement, you can do this. So the intersection between the linear response and the linear spectrum will tell you that displacement will be somewhere here. Well, for the softened, more damped, yielding structure, the displacement, it's about the same. Right? And say the book on displacement-based design by Priestley and Calvi and so on, is based on this idea that you need to increase the damping and work with the nonlinear system. Again, that was the idea of the substitute structure that Shibata and Sozin proposed. And Priestley, Calvi, and Kowalski referred to that in the book. What Sozin realized later, and my suggestion here is, why do all this? Why try to increase the damping? It's not easy. Why to work with the yielding structure, where you're going to get a displacement that is almost the same that you would get if you assume just linear response. If you just work with the spectrum for little damping, whatever that is, 2% if you want to be conservative, 5% if you want to go to the casino too and gamble. Anyway, if you work with the spectrum with little damping and the linear system, things are so much easier. And you're going to get about the same answer. So that's the suggestion, that's the basis for what Sozin did. Questions about that? Because what all that means is we can just estimate the initial period of the structure, go to the linear spectrum, obtain a spectral displacement, and if I can project that to whether the roof or some floors up in the building, I should be able to estimate story drift. And the data seem to suggest that the mode shape is a good vehicle. The mode shape that we get from linear analysis is a good vehicle to understand how the drift is distributed along the height of the building. And that's all I need to be able to handle to do displacement-based design. I need to be able to handle a straight line, I need to be able to calculate the period, and I need to be able to project this ordinate to the building using the mode shape. Does that make sense? Okay, so if that makes sense, what I want to do next is calculate the period of a building and the mode shape of a building so we can use it and do an example. We need to do some numbers here. Otherwise, this is not a class, right? A class without numbers is a seminar, a presentation. Does this work? Better make sure that tomorrow I also bring a shirt that has a pocket. Don't get in trouble. All right. Yeah. So, I've already posted online a document that calculates the period of a frame to begin with. Once we have that, we can calculate the period and the mode shape of a wall, and then we can compare. Then we can do the frame and the wall together. We can have a lot of fun with that kind of thing. You tell me, we can just go through these calculations here just by reading what's already posted, or what I frankly prefer is that we start from scratch. We pretend we don't have the numbers, and we just discuss the numbers as we go. I find that more fun. At least for me, it's more fun because I don't just read. It forces me to think a little bit. So I'm going to keep these calculations that I already have down here where you don't see them, but I do. And I'm going to start my calculations from scratch. This you can then follow with your own notes, or again, starting tomorrow, you could follow this on your own laptop, doing your own calculations. Okay. So let me describe for you the moment frame that I have for you as an example. Again, my goal is to calculate period and mode change because that's how we're going to try to estimate drift. So this is the frame that I have for you as an example. 7 stories. Ah, that's not the frame. Let me see if I can do this now. Okay. There we go. So 7 stories. Story height is 3.65 meters. We have 3 spans, a little over 9 meters each. We're going to calculate the period of this thing. I have the story mass is 145,000 kilograms, or 145 tons. That's per story. That's floor mass, if you will. I also have to give you some dimensions. The columns are 75 centimeters by 60. So I'm going to enter that here as, let me double check that mass. I don't want to get that wrong. Yeah, that's right. Okay, so the columns, I'm going to speak of the columns in terms of their moment of inertia. I'm going to say the moment of inertia of the column is 1/12 times the width, which I'm saying is 600 mil, and the depth is 750 mil. $750 mil. Do you guys use this software at all, or similar software to do calculations for your homeworks and so on? No?
Excel.
Excel. Well, with all due respect, Excel sucks. Well, no, Excel was great for many years, but this is much better. This is much better for many reasons. In my mind, a very good reason is that it handles units. Excel doesn't, so you have to have everything in consistent units, which is not always easy. The other thing is that this is very easy to read, right? This is not cell C12, you know, it's mass. And following formulas is also easier. You can also plot things that run out here, very easy, and you can do sort of recurrent calculations. This is very powerful. I highly recommend this software. There are competitors that are very good too. This is again called MathCAD, but there's also software called BlockPad. BlockPad, very similar, very good. And there's also another one, Russian version called SMAT. SMAT. They all have a free version, and all you need is a free version. So there's really no reason not to use it. And in fact, one reason to use it is you don't have to buy Excel. If someone is paying Mr. and Mrs. Gates money to use Excel, right? So why give him more money? This is pretty good. And again, free. Let's talk about the moment of inertia of the girder. The girder is 600 by, no, sorry, 450 by 900. So I'm going to do the same, 112 times 450 millimeters. And the girder is 900. Deep, pretty good sized girder. Get that? I'm going to modify this to take into account the fact that the slab is connected to the girder and it's going to increase its stiffness. I'm going to do that in a simplistic way. I'm going to put a 2 there. So this is another very nice thing that you can do here in MathCAD. You can really use MathCAD as a Word editor too. You can really create nice looking documents that you can submit as your calculation document. So you can do things like this where you say this is moment of inertia of the column, and so on. I'm not going to waste too much of your time with my annotations. I already produced calculations with full annotations. So I'm just going to concentrate on the numbers here, and I trust that you're taking good notes there, so if you're following what I'm saying, you know what is what. You might be wondering, wait a minute, why are we going to try to calculate the period of this building by hand? I can use ETABS, right? Or I can use SAP, why not? Yes, you can. And nothing wrong with that. Except, how do you know that the number you get is right? It's so easy to punch the wrong number in ETABS, right? Or like it happened to me the other day in that software that I showed you from Japan, Stera. What was the modulus of elasticity? The software didn't say. You were not asked for the modulus of elasticity. You were asked for F prime C, the concrete strength, but not the modulus of elasticity. I looked through the entire manual, which today is very easy, Control F, look for the word modulus, not a word about the word modulus. There was a formula in the background of the code that comes from the Japanese building code that the programmer, Dr. Saito, had assumed. Well, how was I supposed to know? So the point is, you can make mistakes, or you might not be aware of assumptions of what's going on in your software. You need to have a way to check. And if we're going to pin everything down on the period and the mode shape, we better make sure that we get those right. Okay? And that's why I'm teaching you a way to check those quantities. Okay, so I've described the structure in terms of geometry. We got the story height there. We might as well store it here as a variable. You will notice that when I declare variables, you don't get an equal sign. You get the colon and the equal sign. Don't let that scare you. That's simply telling the program you're defining a variable, as opposed to extracting a value from a variable. So for instance, I declared the variable h there as 3.65 meters. I can extract a value out of that variable. Let me make this easier for you to read. Once I declare h, I can ask the software, what is h? And of course it'll tell me, well, h is what you just told me, but look at this. You can, if you don't like meters, if you're like me, and you got used to feet for whatever reason, yeah, you can get the number in feet. You just say feet. Pretty cool, eh? How about this one? This one makes minds flip. Say 1 kilogram mass times 1 G, or just G, is that. No surprise there. But how about this? Maybe it's obvious to you if you're used to working with kilograms force or so on, but I've seen many students confused by this and saying, wait a minute, isn't that supposed to be 9 point? No. That's right. It gets the units right, it gets the physics right too. Very useful. Let's declare here also the span, which is 9 and change. And I think we got everything. We got, no, the other property I need to give you is E, and what did we assume here? E was 25 gigapascals or so. Yeah, 25 gigapascals. Okay, so we have dimensions of everything, columns and beams and so on. We have spans, we have story heights, we have masses, and we have the stiffness of the material. We have everything that we should possibly need to calculate the period of this building. Again, we're going to pretend we don't have ETABS or SAP or whatever it is. We're going to pretend we need to check the result. What do? What we're going to do is Well, first we're going to try to remember sort of high school physics, and then we're going to try to apply high school physics to this. Okay. High school physics. In high school, you probably remember, you were taught about these concepts of kinetic and potential energy, right? Okay. So what we're going to say is that, well, first let's think of a single degree of freedom system, which is much easier to digest, and then once we digest that, we can think of the multi-degree of freedom system. So let's make a little note here on the side and say, for an SDOF, so an oscillator that is vibrating, let's say it's vibrating freely, so we don't have to worry about damping, dissipating energy, and so on. So for this oscillator, there will be a moment when the mass stops, right? And then it comes back and goes through the origin, and so on. When the mass stops, that's the moment where the oscillator has maximum potential energy, right? The spring is stretched the most. When the oscillator goes back to the origin, the spring is not stretched, and all the energy has become kinetic, right? And if we assume there's conservation of energy in the system, then those two values, the maximum potential energy and the maximum kinetic energy, should be equal. Let's say that. The maximum potential energy, again, in a single degree of freedom system, well, it should be about this much. Right? Maximum potential energy. And we're going to equate that to the maximum kinetic energy, which will be how much? Oh, come on. Anyone? David? I met David a second ago. Which David? Did he leave? David. Maximum kinetic energy. 1/2 times the mass, right? Times the velocity squared, right? Yes. And the question is, what's the velocity? Well, if the oscillator is describing sort of sinusoidal periodic motion, then the velocity and the displacement are related to one another by omega, right? If x of time is sine of omega times time, when you differentiate that to get velocity, you get omega times the amplitude times the cosine. So the long story short is, as you may remember from dynamics, the velocity is related to the displacement through the circular frequency. That'll be the peak velocity if this is the peak displacement. Peak velocity if this is peak displacement. This is peak displacement there. That's conservation of energy there for you for a single degree of freedom system. Again, potential energy, peak potential energy equals peak kinetic energy. What a powerful statement, because it tells you that the frequency of the system, omega, doesn't depend on the amplitude of the displacement. To this date, that still bothers me. Yeah, you have an oscillator, if it's doing small oscillations, it takes the same time to complete a cycle as if when it does big oscillations of big amplitude. How does that work? Bothers me to this day. So the delta drops. That's what I'm trying to say. And then you get, of course, that omega. Omega is equal to, by the way, I'm typing a different type of equal. This equal I just get when I press equal, or the colon key. This fat equal is called a Boolean equal. It's just for show, symbolic. So that you get with control equal sign. All right, so that just says that omega is just the square root of k divided by m, which all of you know. But I think it's very cool to look at the problem here. Instead of solving the differential equation of motion and all that mess, just look at it from the point of view of energy. The problem is very simple this way. All right. So what I want to do now is apply this concept to my multi-degree of freedom system. I'm going to imagine the building. I'm going to imagine the building looks like that. Not distributed masses and many springs, if you will, but I'm going to try to condense, idealize my system into a series of balls or masses, concentrated masses, and a single spring representing each story. Because if I do that, and I remember conservation of energy, I should be able to assume a displaced shape, look at the potential energy and those springs associated with that displaced shape, and then look at the kinetic energy of the same system as it comes back to the origin. I'm going to try to apply the same concept that I just applied to a single ball and a single spring. I'm going to try to apply it to the whole thing. Many balls, many springs, many masses, many springs. To do that, I need to, again, concentrate the mass and the stiffness for each floor and each story. I'm going to be very careful with the way I refer to things here. This is a floor, or a level. This is a story. Story is the space between floors. I want to refer to this as a story. I'm going to refer to the spaces between floors as stories, and I'm going to refer to floors as floors. Okay. So how do I idealize the stiffness of each story with a single spring? Arnold, do you teach that here? There is this formula that apparently is also more than 100 years old that was used, I understand, in the East Coast, in Boston, East Coast of the U.S. In Boston area, I think that formula was picked up by Sozin, of course. Don't know how, and he gave it to Arturo Schultz, one of his students. Now he's dean, or no, department head at University of Texas San Antonio. And I think Arturo tested the formula, compared different versions of it, but it's beautiful. It says this: the stiffness of your typical story here has this shape. Of course, there has to be an E there, modulus of elasticity. There's an H, story height squared, and there's a 24 there. Let me make sure I don't go too far off track. No, I got the 24 wrong in the H, in the wrong place. Of course I did. Yeah, H doesn't help stiffness, does it? H hurts the stiffness, and the 24 goes in this numerator. I wasn't following my notes. Sorry. Anyways, yeah, that's better. That's how the formula goes. That starts to look familiar. You know, the one thing that might come to mind is the 12 E I over H cubed that you would get for a fixed column. This is starting to look a little bit that way, but then they do something else here. They say, multiply this times 1 over, and then they do 1 over something plus 2 over something for the columns. And for the beams, they have a 1 over something, and then they have a 1 over something. Like that. That's the formula that Schultz tried, and it turns out it works very well. This first term refers to columns in a story. Again, we're calculating the stiffness of a typical story, so this first term refers to the columns. This second term here refers to the beams above that story, and this refers to the beams below that story. And what they do is they simply add the stiffnesses of those. So say in our building we have 4 columns. So that's 1, 2, 3, 4. What is it? E, 2, 3, 4, 4. I only got to 3. They were trying to close the door at the gate at the lab, and they had to activate 2 things at the same time. They kept counting to 3, but backwards. So I only got to 3. Listening, trying to learn. Anyways, yeah. What we're going to do is we're going to sum the stiffnesses of the column, like that. Yeah. And then we're going to sum the stiffnesses of the beams above, which are 3. We have 4 columns, but we only have 3 beams. The stiffnesses of the girders above. And then that's the length of the girder. And then we do the same for the girders below. Oh, by the way, this is another nice thing that you can do in MathCAD. You can do Control-C and Control-V. Copy, paste, easy. And then stiffness is probably best in kilonewtons per millimeter. So we get 227 kilonewtons millimeter. Cool. That's a typical story. Amazing. Such a simple formula boils down all the beams and columns of that entire story to a single spring, a translational spring, if you will. And then we can do the same for the bottom story, but being a little bit more careful. The bottom story is different, because the bottom story doesn't have beams below, does it? The bottom story has, again, if this refers to the beams below, the bottom story has a big foundation below, right? So I'm going to assume that big foundation is very stiff. So I'm going to say this term is a 0, right? I'm going to assume this is almost infinity for the foundation. So I'm just going to drop that term for the first story, which will increase the stiffness some. To keep my notation simple, I'm going to call the ratio of those stiffnesses alpha. I don't know why we like Greek letters to call variables or their, I don't know, sounds fancy, I guess. It makes it sound like Plato, maybe. But I'm going to call that ratio alpha, like that. Oh, I should call this a different name, shouldn't I? That was a typical story that I had above. I'm going to call this the ground story. Let's call that the ground story. So what I want here is the ratio of the stiffness of the ground story to the typical story. 40% stiffer. Not trivial. Okay. Well, I have boiled down my 2D structure. Of course, in a real frame you have, in a real building you have several of these frames, right? So in a way you could argue that I'm looking at just one sort of representative frame of many, and the mass I gave you, 145 kilograms, 145,000 kilograms, that's just the tributary mass for one frame, right? But I boiled down that 2D problem to a 1D problem, if you will, with one simple equation. How good can it possibly be? You know, it's quite the approximation. All right. Well, we'll find out here pretty soon. What I want to do now is, again, introduce a deflected shape here. I'm going to assume that I know how this thing vibrates. I'm going to assume a mode shape. That's going to allow me to calculate, again, potential energies when the thing is displaced the most, and that's going to allow me to calculate kinetic energies when the thing is back at position 0. And I'm going to equate those two energies, and that's going to give me the frequency, just like I did for the SDOI. So that begs the question, what's the deformed shape of this thing? What's the mode shape? Well, I don't know. we could assume maybe a linear shape, and that will get us going. But an easier thing to do is to apply some forces. You know, we have a series of springs, so it shouldn't be hard to apply some forces and see how this thing deforms. And that's what I'm going to do next. I see we have 5 minutes to go, but I don't know whether you have a tradition to stop a little earlier or not, or you go to the hour. This varies.
Up to you. Yeah.
I don't know, if it's up to me, we stay the day here.
You can try.
Good luck. All right, so let's see if we can get the problem set up and make a little bit more progress. So again, really what I need is a deformed shape. But to obtain a deformed shape, the easiest thing is just to apply some fake forces and then see what the deformed shape is. So don't get confused by that. I'm just going to define some force distribution. So I'm going to define some arbitrary forces to help me estimate a deformed shape. That's all I'm going to do. And I'm going to do that by making use of something that is very powerful in MathCAD and similar programs, which is I'm going to use something they call a range variable, which goes more or less like this. I just want a counter, so to speak, that goes from 1 to the number of stories I have, which is 0. Easy. And what that does is it creates a series of values. Pretty cool, eh? I think it's pretty cool. And that's very useful because that allows me to do things like this. I can say define these fake forces. Again, these are arbitrary forces. I just want a deflector shape. In fact, we can do this assuming the deflector shape is going to be the shape of a sinusoid or a quarter of a sinusoid. And you'll see actually that's pretty close to the actual shape. So we could just start from there. But anyways, for whatever it's worth, I'm just going to define forces like this. It can be anything. But the beauty of using this type of thing is that I don't have to define a vector with 7 values. I just use the power of the range variable like that. I need to be careful here and not confuse you by pointing out that in MathCAD you have different types of sub-indices. Well, strictly speaking, you have a sub-index that you can use to refer to an entry in a vector, or you could also use a subscript, which is just for decoration, right? So when I say something like f prime sub c, then I can obtain this with control, then the subscript thing. Everything has a way to, you cannot access all these things with these operators and so on. There's a way, sort of a graphical shape or way to get any of these things, but I just know the shortcuts to get to these things. But I don't want to bore you with that. But if I say f sub c, this is just a subscript. It's just cosmetic. It's for appearances. This lowercase value there, or the little subscript. This is a sub-index. It's different, and you can see this has a little left bracket there. That's to remind you with control and the left bracket you can get the sub-index. That refers to an entry in a vector. So those two are very different, the subscript and the sub-index. You see, the result of this is that I can show you my forces F like that. And I put a transform sign there to show this horizontally because that takes less space. And you can make this kilonewtons if you want, a little less ugly. And what I want to do next is just push this series of springs sideways with these fake forces and see how much displacement occurs. Because again, with that, I'm going to be able to find the frequency of this thing. How do I do that? Well, I have the forces. From the forces, I can get the shear in each story. shear divided by stiffness gives me the distortion of each spring. Easy. Shear in, let's call it capital B. Shear in story number I should be the summation of the forces above level I. Like that. That should be shear. I'm summing the forces from level I, wherever I'm trying to calculate the shear, and above, all the way to the roof. That should be shear, right? And if I have the shear, again, I can get the distortion. These are not the displacements, but the distortions, the relative motions between the two floors for each level by simply dividing the shear by the stiffness. Yeah. But that is going to force me to decide which stiffness, because I have two values. So there's an easy way to do that, but I'm already a couple of minutes past the hour. So let me just stop there and just point out that when you type something that you haven't defined, I never defined K as a vector. I defined K typical and K ground, but I never defined K. When you define something that has, or you try to use something that hasn't been defined, Mathca tells you you're wrong with a red box. When you define something that has already been defined, Mathca gives you a green box, meaning, hey, you're going to overwrite a previous definition and so on. But we'll pick it up from here tomorrow. Don't lose perspective. I hope I'm not sort of confusing you too much. The point I tried to make here today is that for more than 100 years, there is evidence that shows that damage correlates with displacement and period. And there's also evidence that says it's okay to work with the initial period to estimate displacement. You don't need to worry about trying to figure out how much a period is going to elongate. So now we're going to try to find periods so we can use it to calculate displacement in buildings so we can control damage. Make sense? All right. So I'll see you tomorrow at what time, Professor Wang? Who went?
2 o'clock?
2 o'clock. Here. Same place. All right.
2 o'clock.
谢谢。